Okay, so I foolishly did class this morning without recording it, so I'm going to do my best to recreate what we did this morning. Okay, so um, here's where we go. Um, so just a little recap. We've been talking about Tobit regression, and the idea is that we have some latent variable, y star, and we're interested in estimating the determinants of y star. Okay. And y star is latent, meaning that we can't observe it all the time. There are some values that we can't observe. In this case, we'll assume that it's censored from below at y equals 0. So anytime y is positive, we can observe it. Y star is positive, we can observe it. But anytime it's less than 0, 0 or less, all we see is 0. So y, on the other hand, is observable. Okay, that's the thing we go out and collect data on. And so our model looks like this. Y is a function of beta 1, and y has a characteristic that if y star is positive, we can observe y. It's equal to y star. And if y star is negative, then y is a 0. And so the thing we observe, y, is an incomplete version or an incomplete representation of y star, because there are some values that are censored, we just can't observe them. We assume that epsilon is distributed normally with mean 0 and variance sigma. Okay, and so that's our basic Tobit model. And using this model, there are really two things we're going to want to be interested in. Two things we could estimate, principally. There are two things we can most clearly estimate, and four things we're going to want to pull out of the model. So the two things are the probability that y is 0, that is, the probability that y star is less than or equal to 0. So how often or what fraction of the time do we observe zeros for the y that we actually observe? And that's going to be the same as the probability that y star is less than or equal to 0, given x. This is probability that epsilon is less than negative beta naught plus beta 1x. And that leads us to this. So we have to do a little statistical digression here. And we'll come back to this. So the statistical digression is this. When we talk about a normal density, the density is this bell-shaped curve, right? And when we have a normal density, it goes by lowercase phi. And so if what we're measuring on the axis is beta naught plus beta 1x, then, and we believe that that is normally distributed, it's going to look like this. And if we choose a particular value of this, call it x bar or x star, the probability of observing a value less than x star is given by the area under the distribution to the left of x star. So this thing is a density function, lowercase theta when it's normal. This thing is a cumulative density function. The height of the density is the probability of observing a value less than x bar. So in this case, probability is up here, and at x bar, the height of the density, this is the probability that this variable is less than x bar. The cumulative density goes by uppercase theta. Okay. Now, I mentioned this because we need to use this notation. The lowercase is the density, the uppercase is the cumulative distribution. And so the probability that y is 0 is given by the cumulative distribution evaluated at minus beta naught plus beta 1x over sigma, which is the same as 1 minus theta, the cumulative density evaluated at beta plus beta 1x over sigma. Okay. The other thing that we might be interested in, and I don't want to spend a lot of time on these technical details. It's not why I'm doing this. I'll show you why I'm doing it in a second. It turns out that understanding what these things mean allows us to get a little bit of intuition about what the Tobit estimator is doing. So the second thing we might be interested in doing is finding the expected value of y when y is uncensored. Okay, so if we only look at the positive values, the values that aren't 0, what's the expected value of y? And so that turns out to be the expected value of y when y is uncensored, turns out to be beta naught plus beta 1x plus the expected value of epsilon. Okay. And this turns out to be, well, the whole thing is beta naught plus beta 1x1 plus sigma times the density function over the cumulative distribution function. Okay. And this turns out to be a term that comes up a lot in maximum likelihood estimation, and so it's worth figuring out what it means. And it has a name. It's called the inverse Mills ratio. It's named after Inverse Mills, and he was actually played second base for the Dodgers. The thing that's never been clear to me is whether Mills is plural or possessive. Sometimes you see it with an apostrophe and sometimes not. What is this inverse Mills ratio? Let's take a look at what it actually looks like. So we will go to Stata, and need to bring up my, I'm not going to find it here. So I'm going to, all right. So now I need to, there we go. Got the graph window showing you now. And so this is the density. This is lowercase v, the density of a variable, which I've called y here, which is normally distributed. Okay. Now, we'll add to that the cumulative distribution function. And so, if, for example, we want to know what's the probability of observing a value less than, of y less than or equal to 0, if we're using the density, we would simply look at the area under the blue line, under the density, to the left of 0. That would be 1/2, since it's symmetric. We could use the cumulative distribution function to answer the question by saying at 0, the cumulative distribution function is going to have a value of 0.5. So the cumulative distribution shows us the probability of observing a value less than the one we identify. And that probability is always increasing because as we move from left to right, the amount of the area under the density is increasing. The amount that we include is increasing. Okay. So the inverse Mills ratio involves the density divided by the cumulative distribution function. And let's see what that looks like. So this green line then is the inverse Mills ratio. And what you can see is that these values are very tiny. But for very small values of y, the ratio between the density and the cumulative distribution function is very large, okay, more than 5 times bigger. Very tiny values, but the ratio is very large. And as y gets larger and larger, the ratio gets smaller and smaller, and it approaches 0 asymptotically. Okay, so that's the inverse Mills ratio. Starts out big, and as y gets larger, as the variable of interest gets larger, the value of the inverse Mills ratio shrinks. So when we come back here, we see then that the expected value of y, when y is uncensored, is this thing, our normal y hat, plus this factor that gets smaller and smaller the larger this gets. Okay. All right. This will come back again. All right, so there are several things we can estimate then, and hopefully I can find the sheet on which I did that before. Alrighty. Okay. So sorry about that. So we're here. Those are the things we can think about the Tobit model giving us. And what I want to do then is to take a second to actually show you what the Tobit estimation looks like. And to do this, I'm going to use a data set that I've used before for labs. This is the NPR data set, which is available on Moodle. At the very top, there's a little link that says data, and this is available there. And I've used this data set for labs before. It includes, it's about how people contribute to their local national public radio station. It has a dummy variable, 1 if contributed, 0 not. And so we could use that to estimate a Probit or a Logit model. And it has contribution amount, individual contribution in dollars. And so there are a lot of people who donate 0 and a lot of people who donate positive amounts. So this is a variable that is censored at 0. And Tobit is appropriate for estimating that. Let's take a look at this variable just so we can see what it is. If we summarize the contribution amount, you can see that there are zeros up to a maximum of $600. There's 3,700 people in this data set. If we get a more detailed view, you can see that the median person in this data set is giving 0, so there's a lot of zeros. And the largest donations are $600, and a number of people, more than a quarter of the sample, gives positive amounts. But there's clearly a huge pile of people at 0, and we need to be able to take that large pile into account when we do our estimation. So to do a Tobit estimation, I'm going to just type Tobit, Tobit, contribution amount, and I'm going to say that's a function of maybe age and person's income, whether they're female, whether they're retired, and maybe whether they're a college graduate. Okay. So those are variables. Now, if I give the command this way, Stata will estimate it, but I've made a mistake. Stata is subtle about telling me about this mistake. I've told Stata to do a Tobit regression, but I haven't told it about the censoring in the data set, and I have to do that. Because right now, STATA has 3,700 observations, and it thinks they're all uncensored. It treats them all as uncensored. Doesn't recognize that there's any left censored or right censored variables. And that's not what I want. I want STATA to recognize that there's left censoring at 0 in this data set. So I need to go back to that command and give it LL. And in fact, I can say LL0, tell it exactly where the censoring is. And now STATA says, I've got 1,200 uncensored and 2,400, almost 2/3 of the data set is left censored at 0, okay? And I get this output, and not quite sure what it means. You know what I'm gonna do? I'm gonna add one more variable in here because there's one other variable I like to put in which makes interpretation a little bit easier. I'll put listen time in there. All right, so now we've got this. And you can see that I've got these coefficients, but given our experience with Probit and Logit, we're a little bit hesitant what to do with these. We need to understand how to interpret these coefficients and how to figure out what the model is telling us. You can see, by the way, that this is again, another maximum likelihood estimator. Starts out with a base value for the log likelihood, and then it has specific, there are actually a bunch of different ways that that computers will look around different procedures that they use to find the maximum value of the likelihood. And there are people who spend a lot of time trying to figure out the most efficient way to do this. So you can see the STATA starts out at -10,000 and eventually settles, converges at this value of -8,500. So that's the maximum value of the log likelihood. And the value, the estimates that we get are here. All right. So that's what Tobit estimation looks like. Now let's talk about what it is exactly that we can get out of this. And I'm gonna go back here. And there are going to be 4 things that we could take out of this regression. One, what's the probability that Y is uncensored? And so that's sort of a Probit-like question. Y is that we observe, the observed data we get are either zeros or positive values. What's the probability that Y is not one of those zeros? Okay. And that probability Y is greater than 0, is given by the cumulative density evaluated at beta plus beta 1x. The thing we're typically most interested in is the marginal effect. And that asks the question, how does a change in x, one of the independent variables, how does that affect the probability that Y is positive? Okay, so that's the marginal effect of a change in x on the probability that Y is positive. So that's one thing we can get out of a Tobit regression. How does a change in an independent variable affect the likelihood of observing an uncensored value? Second thing we can get is the expected value of Y when Y is positive. And so that's the expected value of Y conditional on Y being uncensored. What's the typical value of Y just taking the uncensored values into account? The marginal effect that corresponds is the change in the expected value of Y over the change in X, or how does the expected value of Y when Y is positive, how does that change when X changes? Or how does a change in the value of X affect the expected value of Y given that Y is positive? Third thing we can get is the expected value of Y unconditional. Y is the thing we actually observe. So unconditional means we take into account both the zeros and the positive values. And we might want to know, as X changes, how does that affect the expected value, unconditional value of y? And finally is the expected value of y star and the marginal effect of a change in x. If an independent variable changes by 1 unit, the expected value of y star changes by beta 1 units. And that's exactly, in fact, the thing that Tobit gives us in its output. So those are the four values that we can identify and try to estimate with Tobit. And in order to get all four of these things, we either have to be very clever with Stata, or we can be less clever and simply add in a piece of software that allows us to estimate all four of those magnitudes. And we're going to take the second track and try to be, and just add the software so we don't have to be quite as clever. So the way to do this is we're going to add a program called dTobit2. And what we'll do is this, we'll tell Stata to go out to the internet and search for it, dTobit2. And Stata says, I found dTobit2, it's here. And this is at a repository where lots of programs of this sort are stored. And so we click on this, and this is what you need to do to install it on your personal computer. Click on that, and I'm going to show you now the screen that pops up. Looks like this. And so this is the dTobit2 model. It estimates Tobit model with marginal effects, and that's what we want. And the files that it's going to install are, the first one, the addo file, is the actual program. And the second one is the help file, which describes the program. Okay. It says click here to install, so you click. On my version, I've already installed it, and so it says already all files already exist and are up to date. Yours is going to show you the program being installed. And when you're done with that, you'll go back to your regular Stata screen. dTobit will be there. And now what you can do is this. We'll go back to the Tobit command I gave earlier. And we'll say dTobit2. So instead of saying Tobit, we just give it dTobit2. And now, here's what Stata gives us. First, it gives us this output table. And you can see that the values there and the values we estimated for Tobit previously are exactly the same. So these are the coefficients. And what we've just learned is that the coefficients give us information about the marginal effect of y star, latent variable. So, for example, the listen time, this says, what we wanted to do when we estimated this is know how listening time affects the amount that people contribute. And this says, taking into account all the zeros, as well as all the positive values, that entire array of latent values, y star, some of which we can observe, some of which we can't. This says that among all listeners, a 1 hour increase in listening time is expected to increase contributions by $2.44. Down here are the other marginal effects that we talked about. The unconditional expected value. So this is the effect of changes in x on y, the thing that we actually observe. Okay, and so the unconditional expected value has lots of zeros and lots of positive values, and this says an hour of listening time is expected to increase contributions by about 83 cents among all people. some of whom contribute 0 and some of whom contribute positive amounts. Conditional on being uncensored. So if we only look at the people who contribute, and that's about 1/3 of our sample, what we would expect is if they listen to an additional hour of NPR, then they'll contribute on average about 69 cents more. And this last row is the probit question. Do you contribute or not? And this says that a person who listens to an additional hour of NPR increases the probability that they'll contribute by about 1%. So this is taking the zeros into account and removing the bias that we would get in an OLS regression. This is simply including the zeros as zeros. This is looking at the people who are not zeros. And this is the probability that you will not be a zero. Okay, so there are 4 different magnitudes here that we can pull out of our Tobit regression. What I would encourage you to do is to take some time with this data set, do some estimation, practice the interpretation. And then when you're done with that, you can go to Moodle where the, let's see, and take you over to Moodle here. If I can figure out where it is. Here we go. Yep. Sorry. That's not it. All right. Just give me 1 moment here and I will get Moodle on the screen. There we go. Pretty exciting, isn't it? All right, here we go. So here's, I'm on the Moodle page. In case you missed this, just want to make sure that you have this experience. Oh man. No, you don't want to watch that game. Sorry. Okay. Reload this page. Hopefully that'll get us where we want to be. Here we are. This is the important thing I wanted to be able to show you.
See you next week. Same bat time, same bat station.
Pay a little extra to go to Trinity, but it's worth it. Okay. So the lab, the next lab is here. It's available to you now. And the data set that goes with it is right here. So I'll show you the lab. This lab is about, oops, sorry. This lab is about smoking, who smokes and how much. It uses data taken from the National Institutes of Health. This is a survey from 2013 on about 56,000 respondents. And what I've asked you to do is to go through it and look at determinants of who smokes and how much. So those both the discrete 0, 1 variable, as well as the censored variable Tobit, for Tobit. Let's take a look, by the way. So I tell you here everything I want you to do. And yes, there is a due date. My plan is to discuss the due date next week. After you've had a chance to look at this, you can let me know what you think. Let's go back to Stata and look at this data set. So what I want to do is to open this data set, the smoking lab. And you can see, let's bring that up here, there are many variables in here. One of the variables is, do you smoke cigarettes now? It seems to me that that's a dummy variable for which logit would be appropriate. And on average, how many cigarettes do you smoke each day? So for a lot of people, that's going to be 0. And for a lot of people, it's going to be a positive number. And so that seems like that's a censored dependent variable. Okay, lots of information in here about when you first smoked, how much you pay, marital status, race, geographic information. This is, I've created down here, they're unlabeled, some education variables. So that's high school, less than high school, bachelor's degree, grad school, male is not female, household income. So these are dummy variables. Show you these. These are dummy variables. This is if income, household income is less than $20,000, 20 to 30, 30 to 40, 40 to 50, 50 to 70, 70 to 100, 100, 150, more than 150. Okay, so that's household income. Family income is a little bit different than household because you can have more than one family in a household. Family income is measured continuously. Okay, and you can see there's a lot of information here. There are a lot of variables, there's a lot of observations. And what I would encourage you to do is to take some time to look through this data set and start to understand it. And then start working on the lab. So just again, just looking here, about 27% of the sample smokes now, about 27%, and on average smoke 3 cigarettes per day, but that goes up to an unbelievable 180 a day. And as is often the case, it's hard to know whether to take that value seriously or not. Let's do this. Let's look at smoke per day. And so there are a bunch of people who report smoking 100 cigarettes. One person, these are the 4 largest values, smokes 180. You can take it literally or not. It's always hard to know. Look forward to your judgment on how to handle that variable. But so take some time to look at the data set, look at the assignment, and next week we will talk about it. I'll take any questions you have, talk about how to work through these problems, and we'll figure out an appropriate due date. In the meantime, stay safe, stay healthy, have a lovely weekend, and I will see you next week. All right.